Welcome back to Code Meets World. Today we're looking at LeetCode problem 417, which is the Pacific Atlantic water flow. So looking at this picture here, the Pacific Ocean is the dark blue, the Atlantic Ocean is the light blue, and we need to find every cell where the water can flow from that cell into both oceans. So all the ones in yellow, highlighted in yellow, are the solution. Because if you look at any of them, so for example, this 5 in the middle, water can flow down, so it has to be less than or equal to what it's on. So from 5, it can go down to 3, down to 2, and then into the ocean. It can also go from 5 to 3 to 1 into the Atlantic. So from this cell, we can get to both oceans. This 4 here, in contrast, can go to the Pacific Ocean by going 4 to ocean, but it cannot get to the Atlantic Ocean because if it tries to go down, it can't go up to 7. Water can't go uphill, and it can't go to the right because this 5 is higher, and there's just no way for it to get there. So 4 doesn't count. And of course, all of the edges that border the oceans are touching them, and the water can flow in there. So I think the cell in the bottom left and top right will always be an answer because they will always touch both of the oceans just by default. Here I've reconstructed the picture that we saw in the problem write-up, and I'm using green and yellow because I think it's a bit easier to see than 2 shades of blue. And so the green represents the Atlantic Ocean and the yellow represents the Pacific Ocean. This problem seems rather involved, and the first solution that comes to mind is we go to every single cell on the island and ask ourselves, can we get to the Pacific Ocean from this cell? And can we get to the Atlantic Ocean from this cell? For example, if we started up here with the 1, the answer is yes, we can get to the Pacific Ocean because it touches the Pacific Ocean. But can we get to the Atlantic Ocean from there? So our neighbors, we can either go to the left or down, and both of those are larger than the value that we're at, and water can't flow uphill. So no, we cannot get from 1 to the Atlantic Ocean. So 1 is not going to work. And we could repeat this same process for every single cell in the grid. In the middle, to illustrate this, when we get to this 4 right here, we ask ourselves, can we get to the Pacific Ocean? And the answer is yes, because we could go to 3 and then to the Pacific. We can also get to the Atlantic by going to 4. Remember, we can flow. The water can flow if they're equal. So we can get to the Atlantic Ocean that way. And so we could mark that cell as true. We can get to both of them. So we could go through the entire grid, marking each cell yes or no, and just taking the ones that are yes and putting them in a list. But this means that we would have to consider every single cell in the grid. So we might ask ourselves, what would be a faster way to do this? And can we solve the problem without exploring every value in the grid? And the answer to that question, I think, is actually yes. We don't have to explore every element in the grid. And here's how we could do that. If instead of starting at a cell and seeing can we get from these cells to both of the oceans, what if we start at the oceans and see how far inland the water can flow? As an example, if we start at the Atlantic Ocean and go to this first 1, from here, instead of checking if we can flow downhill, we have to look, are there any cells around us that are equal to or higher than this cell is? Because that means the water could have flown from there. So 3 can flow to 1. So that means when we're on 1, we're looking for any cell that's larger or equal to us. So the water could actually go to each of these cells. And let me actually use a color here. So the water could go from 1, it could go to 4, it can go to 3 and 5. And then when we're looking at the 3 here, we ask, can the water go to 4? It can. Can it go to 5? Yes. And 4 also yes. So in this case, the water can flow here. It can keep flowing to all of these cells. So now the water has gotten to all of these ones. And we can continue doing that until we've filled the entire grid with as far as the water can go. We can do this for both sides, so we can see how far the water from the Atlantic can flow in and how far the water from the Pacific can flow in, and then we can just look, where do these two groups overlap? And finally, the reason why this is better, as I alluded to earlier, is what if, for example, the water from the Pacific, and this isn't actually correct for the problem, but pretend that the two groups are like this, and the only overlap is here on this 3 cell. Just pretend this is the example. Look at all the cells that we didn't have to explore. We didn't have to look at any of these other cells. So using this method, we can potentially save a lot of time by only exploring the minimum number of cells to find the overlap in where the water can flow. Now I'm going to give an example of how this might actually work. If we think of it as a search problem, either breadth or depth first search, though I think breadth first search is probably better. What we can do is, and we'll do this twice, once for each ocean. So let's start with the Atlantic. First, we can insert all of the values that touch the Atlantic Ocean into a queue of some sort. And then we'll process them one at a time, and we'll search out from every single one of those cells to see how far the water can go. And we'll keep track of how far inwards the Atlantic water flows in some sort of set. So we can keep track of all the cells that the water makes it to. So an example of what that would look like is, and I'll mark it in green. So the water would start at all of these cells because we would insert them all into the queue at the start. So the water can get to all of these places. And then again, we have to look for any cells that neighbor these that are equal to or greater than, because the water could flow down from those cells to these cells. So in that case, we get this 4 because it's equal to its neighbor. This 3 is larger than the 1. This 4 is larger than the 2 down here. This 1 is equal to the 1. The 7 is greater than both of its neighbors. The 6 is also greater. And do we have any others? I don't think so, because 3 is less than both of these. 3 is less than 4. Oh, we can go up to the 5. So we have to also mark, because we can go from 3 up to 5 or 1 up to 5. But from the 5, these are not greater than or equal to, so we stop. And same here, these are all less. So the Atlantic water would flow to all of the cells marked in green. Now let's do the same thing for the Pacific Ocean. So firstly, we will mark all of the ones that border the Pacific Ocean as yellow, just like we did for the green. And you'll already notice that this cell and these 2 cells, so these 3, these ones are all going to be in our final solution because they're already being touched by both colors. But to finish out the problem, we'll ask again from each of these yellow cells, if a neighboring cell is greater than or equal to it, we can extend our search to it. So starting from this 5 down here, there's not really anywhere else we can go because 1 is smaller and 6 we've already been to. From the 6, we can go up to this 7. From the 2, we can go up to the 4. From this 2 up here, we can go to this 2 because it's equal to it. From this 2 here, we can come up to this 3. And then we just have to ask ourselves from this 3, or actually we have to also look from this 5. So from this 5, we can't go to the 4 because it's less. 3, we can't go to the 4. From this 3, we can't go to either of these. From this 4, we can go up to the 5. We can also go up to the 7, but we already tracked this one. So just the 5 we have to mark. And then are we finished? From the 7, we can't go anywhere. And from the 3, we can go up to the 4 here. So I think we can also mark that one. So, and then if we've marked that one, we can go from that 4 to this 4, again with the yellow. This probably would have been easier to show if I did one color on one graph and then another color on another graph and looked at the overlap. But hopefully you can see that the cells that are both colors end up being the ones I'm circling in red. And if we compare that to the solution that we were shown in the write-up, this looks correct. First, we can define all of the various data structures and values that we're going to need to solve this problem. So I'll start out by setting rows and columns just to equal the length of heights and the length of the first row of heights. And this way I don't have to keep putting in length of heights every single time I need to reference the row and column. Next, I'm going to need for both oceans a queue to keep track of my breadth first search. So we'll have a queue, which will stand for Atlantic queue, and we'll have Pacific queue, and we'll set each of those equal to a empty deck, and then we'll populate each of these decks is the first step of the algorithm. We're also going to need a set for both of the oceans to track which values or which locations we have seen. So I'll call that Atlantic scene and Pacific scene, and these will both be an empty set that we will add values to as we see them. And finally, we need a way to keep track of where the water has been. And that's different than scene. Scene is keeping track of every node that we've considered, but not every node that we consider will be a place that the water can reach. So I think we also need an Atlantic reached and a Pacific reached. And I think I can make both of these a set as well and just add to it as we find places that the water reaches. Now we're going to go through and populate the AQ and PQ. So we need to add all of the values that are on the upper or leftmost edge to the PQ, and all the values that are to the right or bottom edge to the AQ. So we'll loop through all of the values in the grid. So we can say for row in range rows, and we can say for column in range columns. So we can ask ourselves if the row is 0 or the column is 0, right? Because if the row is 0, we're up here, and if the column is 0, we're down here. So both of those indicate that we would be touching the Pacific Ocean. So we can say that the PQ, the Pacific Q, is going to have that value appended to it. So we want to add all the values that touch the Pacific Ocean to the Pacific Ocean's Q. So we can say, well, we need to save the coordinates of that location because we need to go to it in the grid. So we can say RC like that. To figure out if a cell is touching the Atlantic Ocean, we can check if R is equal to rows -1 or column is equal to columns -1, because in either of those cases, we would be at the right or bottom part of the grid. And so in that case, we can say Atlantic Q dot append, and just like above, the row and the column. Now that both of the queues for each ocean are populated, we now need to conduct a breadth first search from each of them. So I'm going to start at the Atlantic Ocean, and we're going to do this twice. So while the Atlantic queue has values in it, we're going to start by popping off the first value in that queue. And so we can set our row and column equal to AQ dot pop left. And then we can say if this location is not in the Atlantic scene. So what this is saying is if we have not been to this value before, we need to explore it. If we have been to it before, we're just going to skip this if condition and we are going to continue the while loop and pop off the next value. So basically, if we haven't explored something yet, we need to explore it. Because we're at a location that we have not seen before, the very first thing that we should do is just go ahead and add that to a scene. So we can say a scene dot add, and we'll give it the row and the column. And because this location is going to fit the criteria to explore, I guess we can also add it to a reached. But as I'm typing that out, maybe I don't actually need the reached cues or the sets. I'm actually going to comment those out because I might be able to do this in a way that just uses the two sets, but let's come back to that in a second. Now that we've added the location that we're at now to our scene set, because we're now exploring it, we need to start from this node and we need to look at all neighbors on all four sides to see if there's anywhere that we can go and explore next. So we can say for we can say for new row, because we already have a row and a column that we're on. So now we want to look at each of the possible new row and new column pairs that are in this list of, and I'll make we need to check 4 new locations from every cell that we're on. So we need to go row +1, staying in the same column. So that would be going down a row on the grid. We need to go row -1 column, which would be going up a row on the grid towards the top. Then we need to stay in the same row and go to the right one, so over 1 column. And then we need to stay in the same row and go to the left 1 column. And for each of these possible locations that we could check, we need to both confirm that we have not gone off the edge of the grid, because we don't want to do that. And we also need to check if that next value is greater than or equal to the value that we're currently on. Because remember, because we're exploring from the water into the middle, the jumps need to be to cells that are bigger than or equal to the value that we start on. So we can say all of this, I think, in one if statement. So if 0 is less than or equal to new row, which is less than rows. So basically new row has to be between 0 and the number of rows -1. And the same thing for the columns. So 0 is less than or equal to new column, which is less than the number of columns. And finally, the value at heights of new row, right, new column, and see, has to be greater than or equal to the value in the grid that we are currently at. So heights are C. Hopefully this makes sense. So we're checking for every neighbor that we explore from a given cell. Have we gone off the grid? That's what all this is checking, that we're actually in the grid. And then the new value that we're jumping to has to be greater than or equal to the value that we're currently at. If all of these things are true, then finally we can say that aq dot append the value or the location at new row, new column. So if we've confirmed that the new value is in the grid and the new value is greater than or equal to the value that we're at, we should append that to the queue, because either we've already been there and we're going to skip it the next time we come through, or we haven't been there yet and we need to add that to our scene set because it's another place that the water can reach. Okay, now I know copy and pasting code is a dangerous game, but in this case, I'm willing to play it because these two loops are going to be absolutely identical, except instead of doing everything on the Atlantic Ocean, we're going to be doing it on the Pacific Ocean. So it is as simple as changing all of the variables from their Atlantic version into their Pacific version, which I think is just those couple there. Hopefully I haven't made any errors. Once we've done all of this, there's just one thing left to do, which is we have to take the scene set for the Atlantic and the scene set for the Pacific, and we have to find the intersection of them. And we can do that in Python by saying a scene dot intersection p scene, and this is going to return a set, which I think is technically a dictionary. So we just need to make this a list to convert that dictionary into a list, and then we can just return that. So after all of this, let's go ahead and run it. Surely there is an error somewhere in here. And yeah, I don't have a colon after that, which probably means I need a colon somewhere else. Oh, actually, that looks good. So let's try that a second time. Oh, I'm missing my and right here. So that's probably going to be the case in both of these. And there we go. This looks to be passing. So let's submit and see if that passes all of the test cases. And it looks like it does. And it looks like it is 92nd percentile, which is awesome. Though this does look like this is about the fastest you can do it. So all of the correct solutions are grouped here on the far left. But that's how you solve the Pacific Atlantic water flow problem. Pretty interesting, and glad I realized that you only need one set there. So you can actually keep track of the values that you've seen, and those also happen to be the values that the water has reached. So hopefully this was helpful, and let me know down below if you have any comments. I will see you in the next video.